Okay, so, all right. So the big ideas in Unit 4, the one we just finished, right? Whose stuff is due when? Friday at midnight. So you'll have through the end of the day to come see me if you have questions, all that kind of stuff. Okay, you guys. Every class except for second and fifth tomorrow is taking a test. So if questions are popping up, I should be able to help you. Okay. But you'll have through the end of the day on Friday to ask questions and then due by midnight, okay? All right, so everything in Unit 4 we talked about was just kind of like basic concepts of probability, stuff that theoretically you've probably seen before several times, okay? The shift of what we're doing today is now we're going to start talking about some of the more complex concepts in probability, okay? So everything, we basically use data in two different ways. We understand what our population looks like and we try to make predictions about the future, okay? Or we don't know anything about our population and we're trying to use a sample to make those decisions. And for both of these things, we use probability as a tool, okay? So probability is an important part of everything that we're going to be doing. All right, so.
For the interruption, just wanted to make a quick announcement.
Whatever. Okay. All right. So essentially, we're going to be operating in units 5 and 6, the one like this one and future ones. We're going to be operating on we know certain things about our population. Okay? And then we're going to try to use that to decide if something is weird, if something is unexpected or not. Okay? And then in units 7 through 11, we won't know anything about our population. And we'll have to use, so we're going to take a sample and somehow try to make those conclusions from a sample. Okay, all of which are going to require probability in some capacity. Okay? So like I said, we're going to be focusing on, in this particular case, that we know stuff about a population, but we don't know, and try to make some conclusions from that. Which means we're going to know probabilities about a population, okay? So we're going to start with what we call random variables. In general, a random variable is a numeric quantity attached to a probability. And I know that feels really weird. But random variables are quantitative variables. So to piggyback on an example I used last week with like the number of stoplights I have to stop at the way home, we could say, oh, I could have 0 stoplights, right? I could have 1 stoplight, 2 stoplights, there's up to 4. And we could look historically and say, well, she has 0 stoplights about 10% of the time. She has to stop 0 times about 10% of the time, 1 time about 15% of the time, et cetera, et cetera, et cetera. Okay? So number of times I have to stop is a numeric variable to which I would attach a probability of how frequently that thing happens. All right, discrete random variables. We've kind of talked about the description of discrete versus continuous. We talked about like discrete variables are shoe sizes and continuous variables are like the actual length of your foot. Okay, another way to think about discrete random variables, they are countable random variables. Whereas continuous are more their range. We would use a range to describe. So, you guys, if I asked you, what does it mean if someone tells you that they're 5 foot 1 inch tall, do any of you believe that anybody is exactly 5 foot 1 inch tall? No. We might say, when someone says they're 5 foot, 5'1", that means they are somewhere between 5 foot 1/2 inches and 5 1.5 inches, kind of like in that range. But does that kind of make some sense to think of it that way? Okay. So some examples of discrete random variables might be the number of lights where Meister has to stop. Versus a continuous random variable might be the height of a randomly selected person. Subtle differences, okay? And again, attached to probability. And when we have random variables, so Unit 5, what we're going to do in this packet is talk about discrete random variables, several different instances of discrete random variables, okay? Tomorrow, Unit 6 will be continuous random variables, okay? And when a variable is discrete, we can create kind of like a table that describes what's going on with that variable. So I'm going to go back to the other day. We did we had 3 coins, right? And we flipped them and we listed out all those possible outcomes. You guys remember this? Okay. And so we had, and then we decided a tree diagram might be a little bit easier to help us see what's going on. And this tree diagram is designed to help us see, for instance, that this branch is heads, heads, heads. The next branch, like if I'm reading those branches from the left, the first coin was heads, second coin was heads, third coin was tails, then heads, tails, heads, heads, tails, tails, and then we have tails, heads, heads, tails, heads, tails. And of these 8 outcomes, because the coin is a 50-50 toss, right? So of these 8 outcomes, all 8 of these are equally likely. But what if instead what I measure is how many of the 3 coins came up heads? Okay? So all of a sudden when I do that, this one had 3 heads. This one had 2, this one had 2, this one had 1, this one had 2, this one 2, this had 1, 1, this last one was wrong, was tails, and this one had 0. So, if I'm flipping my 3 coins all at once, right, what are the possible outcomes in terms of number of heads? What? I'm going to do 0, 1, 2, 3 because I like to count up, but okay? And of those 4 outcomes, are they all equally likely? No. What's the probability of getting 0 heads? 1 in 8. So do you guys mind if I call that 0.125? Yes. And then of getting 1 heads? 3/8. 2 heads is also 3/8. 3 heads is 1/8 again. Now, if a variable is discrete, we can create in some way a table that looks like this. Okay? That lists out every possible outcome and each of those outcomes' probabilities. Okay? And are you guys with me that getting 0 heads and getting 2 heads are mutually exclusive from each other? Because you can't flip those 3 coins and get 0 and 2 at the same time. Okay? All right. Now, when sometimes we like to think through, we want to make sure what we have is a legitimate probability distribution. If a probability distribution is legitimate, then you should be able to add together all the probabilities. And if it's legitimate, you have every possible outcome listed out separately with its probability. So if it's every possible outcome, what should all the probabilities add up to? 1. So I know this is legitimate because the probability distribution adds up to 1, or the probabilities of the distribution add up to 1. You guys, could we use a table like this to say, if I gave you this table and say, what is the probability that you get at least 1 head? Could we use this table to figure that out? How would you figure that out? Okay, so what's the answer?
0.375.
I want at least 1 heads, yes? So not, because that's the probability I get exactly 1, right?
So would you add 1, 2, and 3?
You could do 0.375 plus 0.375 plus 0.125, right? We could say, well, that's either 1 or 2 or 3 heads. And or we learned yesterday with the, or was it yesterday? Monday, we learned Monday that or means you add probabilities. That's the addition rule, right? They're mutually exclusive, so we don't have to subtract any overlap. Is everybody good? Okay, now we can draw histograms of probability distributions just like we did of like raw sample data. Okay, the only difference is now, so our x-axis is going to be the number of heads. That's what our variable is. That's what we're describing. And instead of my y-axis being frequency or relative frequency, my y-axis will have to be probability. Now, a reminder that we kind of said at the beginning of Unit 4, probability is how frequently something should occur if we do a large number of trials. So probability and frequency go hand in hand with each other. Okay. I'm counting up by 0.125. I'm counting up by eighths. Okay. By eighths, not eighths. You make me do that. All right. You guys. In the minute I have a histogram, I have shape, center, and spread. So this is a really good opportunity for us to review these concepts. Okay. You guys, when I look at this histogram, how would you describe this? Kind of bell. It's a little bit, without getting into the weeds, it's really hard for a discrete distribution to be bell-shaped. It's too clunky, and I couldn't like make I couldn't change the width of these ranges of these intervals, right? Because it's not like I can have like 0 to 0.5 and then 0.5 to 1. Like it doesn't make sense to make it. There's not much I can do to smooth it out. Okay, so if you called this bell-shaped, I probably wouldn't mark you wrong, but I wouldn't agree with you. I would just say that it's mound-shaped and symmetric.
Can Braddock Lusher please report to the office? You're leaving for an appointment. Braddock Lusher, please report to the office. Thank you.
But I'm already making a recording. So. So you'll have to fast forward the first few minutes. But I'll have it up and on Schoology for everybody else anyway. Okay. You guys, in this picture, the mean and the median are equal to each other. Don't forget your phone. Okay? You guys, what are they? Like, if you had to guess, what is the middle of this, what would you say? Yeah. Now, it is not possible for us to flip the 3 coins and get 1.5 heads. Are we all comfortable with that? That's like not a thing. That doesn't mean that, so when we find the mean of a probability distribution, it's what we would expect to happen. So sometimes we call it the expected value. It's what we would expect to happen over a large number of trials. Okay? Do we all agree that, okay, so here's my mean. And in reality, like if we actually did this a bunch of times, we would have values here. They wouldn't be perfect, but we could have a dot plot that we could think through that we would have this dot plot, yes? Okay, and each of these points has a deviation from the mean. Some are really close, some are really far. Okay, which means it has variability. It means it has a standard deviation. It has an IQR. It has a range. For right now, I would describe the range of this one because that's what the values I've got are the max and the min. Okay. All right. So, because discrete variables have shape, center, and spread, okay, we need to learn how to calculate those things. So, in this particular case, so like I said, so we call the mean the expected value. So I'll probably use those two terms interchangeably. Okay, so I might say what is the mean. I might say what is the expected value. The two things mean the same thing. Okay, so the way we put these into the calculator is very, like the way we calculate these is very similar to what we have done in the past. So what I'd like you guys to do is put the x's in L1 and the probabilities in L2. While you guys are doing that, I'm going to put it in my calculator and get it set up. So you guys can see. Let's go ahead and make this video. All right, and guys, while I'm doing this, can you remind me, how would I have found the mean and the standard deviation before? What did we do in the calculator to find all that information? So you start with hitting stat, so what we're going to do is hit stat. You're going to arrow over to calc, you're going to choose the one variable stats. And now, the frequency list can be a list of probabilities in the same way it was a list of actual how frequently each thing happened. Okay, so go ahead and make your frequency list your L2 by hitting second 2. So you guys, what is the expected value in this particular group? 2.823. It's just the mean. Now, talk to me about the standard deviation. What's our standard deviation here? That looks like it 1.697, yeah? Okay, you guys, how come there isn't an S? S is the standard deviation of a sample. If I have a list of probabilities, this isn't from a sample. This is an example of we know something about our population and we're trying to make conclusions about future samples. Everybody with me on this? Okay? So when what you give the calculator is a whole bunch of probabilities, it knows you're describing a population and not a sample. Okay, does everybody see where it says n equals 1? What does that mean? It means the sum of n is the sum of my frequencies. So, is this a legitimate probability distribution? Yeah, because all the probabilities add to 1. So do you see how you can find the mean and the standard deviation of these in the calculator in the exact same way? Okay. There we go. This takes forever to upload one of the videos. Okay. The other thing I'm going to ask you guys to do is decide, are certain events unusual? Okay, unusual events and the way we're going to deal with them with random variables are more than 2 standard deviations from the mean. So that symbol means standard deviations. Okay. Like I said, we can use this table to find probabilities. If I ask you based off of this table, what is the probability that whatever this variable represents is more than 5.7, greater than or equal to 5.7? When I look at this table, what does greater than or equal to 5.7 mean? That could be this group or this group.
There's 2 out of 7.
So what do I do? Well, so are you with me that means I could do that? That either means 5.7 or 5.9? And then what do I do with probabilities for or? I add them. So we could say, well, that means 0.09 plus 0.05. So the probability that I pick one of these things and it's greater than or equal to 5.7 is 14%. We're just adding those sections of the probabilities. All right. If I want to decide are events unusual, we just said that means more than 2 standard deviations from the mean. So something can be unusually small or unusually big. I was about to make short, tall references again. Okay, so what we're going to do is we're going to take our mean plus 2 times our standard deviation, and our mean minus 2 times our standard deviation. Math, when you have those numbers, can you shout them out for me, Bob?
Yeah, 6.217 for the bigger one. Negative 0.571.
Okay, so I look at my outcomes, you guys. Are any of those numbers outside those range? All right, so for this one, nothing unusual. Everybody good? Okay. Find the probability we get a value of 1.75 or less. Are you guys comfortable with me calling that x is less than or equal to 1.75? What would we do here?
0.26 plus 0.13 plus 0.10.
We're adding the probabilities for the outcomes that are less than or equal to 1.75. I think that's 0.49. Okay, so from here, I would like you guys to try this page. Those of you at home, I'm gonna pause the recording, so go ahead, pause. Try on your own. And I'll put my answers in, you guys put your answers down, and then we'll compare in a little bit. Just this is me making sure you understand what's going on, okay? How are we feeling? Okay, so you wouldn't need, for this last question, guys, you could answer it one of two ways. We all good? Okay, so there's one other thing I want to do, just a real quick side question, not related to this table, but to a different table that I'm about to give you. Okay, this is me laying some groundwork for what is the most challenging part of what tomorrow will look like. Okay, something that students traditionally struggle with. And so I just want to show it to you, okay? All right, so let's say very similar thing where we have 0, 1, 2, 3, 4, but it's not selling cars, it's something else, okay? So we have 0, 1, 2, 3, 4. We'll call it the number of stoplights on Miss Meister's ride home. That's fine, okay? And here's the information I'm going to give you. That this is 10%, this is 15%, this is 30%. Okay? And 0 through 4 are all the possible outcomes. Is everybody with me? So I'm not going to tell you the probability of 3, and I'm not going to tell you the probability of 4. But I want to know, what is the probability x is greater than or equal to 3? Is everybody with me? Okay. So how do I answer this question when those are the two probabilities I didn't give you?
Add up probability and subtract off.
So we're all comfortable that the total of those probabilities is 1. And we know that the total of these probabilities is 55. So in your guys' head, we can do 1 minus that 55%. And in reality, what you just did is 1 minus, how do I describe what that 55% really is? That was the probability that x was less than or equal to 2. So to find the probability that x is greater than or equal to 3, we can do 1 minus the probability x is less than or equal to 2. Is everybody good with this kind of reasoning process? And we can see that pretty clearly on this table. It's easy to see. Okay, great. Yeah, and then, of course, we can tell then that the answer is 0.45. I'm not worried about getting to the 0.45 right now. I want to make sure we understand that this and this are equivalent statements. And for those of you at home that can't see where I pointed, let them see right here, that this statement and this statement are equivalent in value. Because that's going to make this stuff, the hard part of what we're going to do tomorrow, a little bit easier. Is everybody okay? Okay, great. I think what I'd like to do, perfect.